So in this class we'll look at multiple access techniques and analog and digital modulation. So what did we do last class? So we looked at fading and diversity. So from the RF system level, there is one more thing which we need to know, which is multiple access techniques. So what does this mean? So it means a number of things. So first of all, you have limited hardware. So you may want to share resources inside a transceiver, and you have limited spectrum. Usually this is in the form of shared bandwidth. So we'll look at multiple access techniques for each one of these. So the first one is called TDD, or time division multiplexing. So what does this mean? So you have a single antenna in a transceiver, and this is used shared between the TX and the RX, which is the transmitter and the receiver. And the important things to note are, so you have direct communication with the peers, that is with the other mobiles. And the second thing to note is your RX and TX are not on at the same time. And we'll also see that if you have a nearby transmitter, it can actually desensitize your receiver. And the last thing to note, your RF switch between the antenna and the receiver is critical. The next kind of multiple access technique is called FDD, or frequency division multiplexing. So if you consider a single transceiver, so you have the transmitter and the receiver, and each one of these uses a specific frequency. So the receive uses the frequency band FR, and TX uses the frequency around band FT. So you have FT being transmitted and FR being received. So the important things to know, you have what is called a base station that converts that performs FT to FR conversion. Okay, and this portion is called the duplexer filter. And both RX and TX can be on at the same time because they use two totally different bands. and you're also here you're worried about the loss of the duplexer. The next type of multiplexing is called FDMA, or frequency division multiple access. So what this means is, you have a given band of frequencies that you can use, and each of the bands is split into multiple sub-bands. Let's say it's split into n sub-bands or channels. The frequency band sub-bands from 1 to n are called the channels, and each user uses a separate channel. What is the maximum number of users? Simultaneous users is, let's call this F1 and F2, so it's F2 minus F1 over n. Rather, it's F2 minus F1 over, let's call this delta F, which is n. So you could run into capacity problems. Next we'll look at TDMA, or time division multiple access. So instead of dividing the users in frequency, they are divided in time. This is user number 1, and you have user number 2, and so on. So you have each user uses a specific amount, uses the spectrum for a specific amount of time, and the user number 2 uses it for the same TS, and so on. Let's call this TS, this is also TS. So in other words, data is transmitted as a burst. Excuse me. And each of these time intervals is called a slot, and all the slots put together is called a frame. So you have the concept of frame and slot, and time synchronization is very important. Now the other kind of multiple access technique we'll study is called CDMA, or code division multiple access. So this works by using a set of n orthogonal codes to separate the different users. So if you look at TDMA is orthogonal in time. Okay, so FDMA is orthogonal in frequency. So CDMA is orthogonal in codes. So how does this work? So let's say at transmitter 1 you have a signal x1 of t, it's multiplied with a certain code c1 of t, and y1 of t is transmitted. At the receiver y1 of t, let's say at receiver 1, which need not be the which is not the receiver of user 1, but it's the receiver which receives tx1. y1 of t is received and also multiplied with the same exact code to regenerate x1 of t. So let's say there is a second transmitter tx2 that transmits a different signal. This uses a different code c2 of t and produces y2 of t. Now at the same receiver, if y2 of t is received along with y1 of t, it is multiplied with the code c1 of t and this produces 0 because the two codes are orthogonal. So the basic idea is ci.cj is 0 for I not equal to j equals 1 for I equals j. Examples of orthogonal codes, you can come up with a number of them. One example is of course 1, 1, 1, minus 1, a 4-dimensional code, 1, minus 1, 1, minus 1, 1, 1, minus 1, minus 1, and 1, minus 1, minus 1, 1. Okay. The other interesting thing is these codes can be used to spread the signal, and this is called spread spectrum. So if you had a certain signal which looks like this in frequency domain and you multiply it with c of t, which is the code, you could get something which looks something like this. Okay, so which is spread in frequency. So what does that mean? It looks like bandwidth usage increases, but users can overlap in frequencies. And other users appear as random noise at the specific receiver. Now the other nice thing is it actually has a soft capacity limit. That is, SNR, as number of users increases above the maximum allowed, the SNR slowly starts degrading instead of not being able to support anymore. Okay, so the last thing we'll look at is OFDM. So this is strictly not a multiple access technique. It's more of a modulation technique, but we'll take a look at it along with these because we are looking at different techniques using different carriers. So this OFDM is called orthogonal frequency division multiplexing. So each of the TX and RX channel bandwidths are divided into many sub-channels, and each one of the sub-channels is orthogonal to each other. So you'll have a number of channels, and this is your, let's say in this case I have shown 3 sub-channels, but you could have a number of them. In fact, several hundreds or thousands are not uncommon. And you could also have guard bands to separate the different subcarriers if you want to eliminate ISI completely, but then you would have lower spectral efficiency. So let's look at some examples. So of systems which use these multiple access techniques. So let's say GSM, it's a cellular technique. So it uses TDMA and FDMA. So remember, these multiple access techniques are not necessarily mutually exclusive. You could use both TDMA and FDMA at the same time. You could split a certain bandwidth into a number of channels for different users and each user can multiplex in time also, and it happens to use FDD. If you look at Qualcomm CDMA, it uses TDMA, sorry, of course it doesn't use TDMA, it uses CDMA and FDD. How about, let's take the cordless phone technology, which is called DECT. This uses both TDMA and FDMA and TDD. And let's look at wireless LAN 802.11g. It uses OFDM and TDD. Okay, so that's as far as multiple access goes. Now let's look at some schemes of analog and digital modulation. So before we start looking at modulation, let's start looking at some terms which we'll use here. So if you have a certain signal around a frequency 0, so this is called a baseband signal. Now you can perform a couple of operations around this. So in the transmitter you do what is called modulation, and in the receiver you do what is called demodulation. So once you do modulation or demodulation, instead of being around 0, your signal now moves around a frequency plus or minus omega c. So this is called a passband signal, and it has a carrier which is omega c. The frequency of the carrier is omega c. Now why do you want to modulate? So the reasons for modulation, so remember RF can be either used in wired or wireless systems. In wired systems you want to modulate because of shielding. So shielding is much better at higher frequencies. And in wireless systems, so one reason is if everybody starts using the same, just transmitting at baseband, there is no talk of sharing spectrum. Everybody, all signals will overlap. So one reason is shared usage of spectrum, and another reason is so that antenna sizes can be smaller. It's usually proportional to the wavelength of the signal you are transmitting. Now a generalized passband signal can be represented as x of t equals a of t, which is the amplitude modulation, cos of omega ct plus theta of t. So this is the amplitude modulation portion, and this is the phase modulation. Okay, and remember that the instantaneous frequency is omega c plus d theta of t by dt. Now let's look at some analog modulation schemes. So first let's look at AM, which is amplitude modulation. So a general AM signal can be written as AC, which is some constant, times 1 plus m xbb of t cos omega ct, and this is your am amplitude modulation component, and this is called the modulation index, and of course it has a constant frequency. So what does it look like in the time and frequency domains? So in the time domain, if you have a certain signal which looks like this, let's say, and you multiply it with the carrier at omega c, this is a baseband signal, and it's multiplied with the carrier, let's say cos omega ct. So what does it look like? So you'll get this, and you get the cosine which is envelope modulated by the baseband signal. Okay, and this is the envelope. What does it look like in the frequency domain? So let's say the signal in the frequency domain looks something like this. So you're going to convolute it in the frequency domain with a cosine which looks like this, which is just two impulses at plus or minus omega c, and this gives you at the signal at plus omega c and minus omega c. Okay, so next how we'll look at frequency modulation. And phase modulation can be thought of as to be very similar to frequency modulation. So the generalized signal x fm of t is a constant amplitude times cosine of the carrier omega ct plus m times integral minus infinity to t x baseband of t dt, and this is called the index modulation fm index. So what does it look like? So if I take a baseband signal in time, let's say it looks like this. So it's going to look like you have a constantly decreasing frequency. So you could have a high frequency signal and then slowly it becomes slower and then it becomes high frequency again. Okay. Okay, so now let's look at, these are the two most simple analog modulation schemes. Now let's look at digital modulation schemes. So there are several different kinds of digital modulations. So one kind is called amplitude shift scheme. Sorry, let me do a better job of drawing this. Have this. So you have 0. Okay. So this is called amplitude shift keying, where so you have a cos omega ct. So the system switches between a cos omega ct and 0. So the amplitude of the signal is shifted from a and 0. Another kind is called phase shift keying. So it could look something like this. So let's say look like this, and then suddenly the phase shifts. Excuse me. So this is an example of, so you have some phase transitions at these 2 points. So the transmitter switches between a cos omega ct and minus a cos omega ct. This is an example of what is called binary PSK or BPSK. And you also have what is called FSK or BFSK. where you could just change frequencies. Something like this. So you have, so the two signals changes between a cos omega c 1t, a cos omega c 2t. Okay, and you can also think of representing these signals on a constellation diagram. So in the case of, so what is a constellation diagram? You're trying to represent the signal, so the signal possible symbols of the signal, sorry about that, in a complex plane. So for example, your ASK, so you only need a single unidimensional signal space to represent this. So you have 0 and you have A. So these are the only two possible signal points. In the case of FSK, you have two possibilities, which is, let's say this alpha 1 and alpha 2. So in the case of ASK, alpha 1 stood for the amplitude. In this case, alpha I stands for frequency. So the amplitude is the same in both cases, A and A, but alpha 1 stands for omega c1 and alpha 2 stands for omega c2. So these are the two possibilities. Now what happens if you have noise in the system? So excuse me. So if you have noise in the system, so let's say it used to look like this. So instead of being absolute 0, you could have something like this, and similarly you could have some noise here, right, on top of this. It's just an exaggerated view. So this is time. So what does this mean? So if you have noise in ASK, this, so if you convert it to the constellation diagram, it would look something like this. So since this noise is random, so you could have a cluster of points concentrated around A, and which corresponds to this portion of the signal, and actually this is a little bit, I should have drawn it better here. So of course the amplitude, you don't worry about the phase, so you could have a cluster of points around A and a cluster of points around 0. Okay, so due to noise, so each time you receive the symbol, it won't fall exactly on A due to noise, but it will fall somewhere around that. So what is the decision threshold? So the decision threshold is the point which divides when you decide to choose 0 or A. Okay, so this happens to be, in this case, the obvious thing to choose is a decision threshold of A over 2, so that any signal you receive which is larger than A over 2 is A, and smaller than A over 2 is 0. Now what happens if you have noise with FSK? So so you have A, so you could, if you have amplitude noise, you could get like this, and you might have, okay, so for now we'll consider only amplitude noise, but you could have cases where the frequency of the signal could get corrupted also, but for now we'll just assume there is amplitude noise. So instead of A, so you get a bunch of points around this. This is alpha 2 and this is alpha 1. So what is the decision boundary? So the decision boundary would be a 45-degree line. And of course, if you have BPSK, that's a very simple case. So if you have so you have minus A and A, so the decision threshold is going to be at 0. Okay. So now let's look at some other kinds of techniques for modulation, which are quadrature modulation techniques. So you have several of them. So the main idea is you represent the signal in terms of cosine and sine terms. So some examples are, you could have QPSK, MSK, 8PSK, and so on. So this stands for quadrature phase shift keying. So one example is the WCDMA signal, release 99 signal. This is called minimum shift keying. So one example is GSM, which uses something called GMSK or Gaussian minimum shift keying. And then this is called, of course, 8 PSK or 8 phase shift keying. So each one of these has a different constellation diagram. For example, QPSK could have something like this, right? So you could have, so different types of modulation schemes allow different transitions. In the case of two transitions, it was a lot easier. You just want to go from minus A to A or from A to minus A, right? Those are the two transitions allowed. If you have more than let's say four signal points in 4 points in the signal space, so you could have transitions, for example, between these two, right? And you could have transitions between these two. And the more the number of points in signal space, the more complex the number of transitions. And the last one we'll look at is called QAM or quadrature amplitude modulation. So before we do that, so just wanted to point out, so one example of this is what is called the edge signal, which is you might have heard of. It used to be called it's an evolved version of GSM. Okay, it used to be called 2G, but 2.5G, but now it's included in the 3G standard. It's an extension of GSM. And then you could have quadrature amplitude modulation, so where you could split the amplitude of the signal into, let's say in this case I'm showing you, so you have 16 points, so this is called like 16 QAM, for example, and you could have 64 QAM and so on. So for this class we'll stop here and continue in the next class. So in the next class we'll look at S parameters and resonant circuits.